The first such circuits we shall examine are referred to as flip-flops. To this point in the You Can Do digital series, we have described 7 of the basic logic gates found in digital equipment. There were the AND, OR, NAND, NOR, exclusive OR and exclusive NOR, and the inverter. None of these logic gates contain a memory, in that after a signal has been processed by the gate, it is ready to be controlled by the next incoming pulse. In contrast, a memory element is capable of remembering its input, even if the input changes. The most basic memory element is the flip-flop. You will be introduced to various flip-flop circuits and their properties. We will begin our discussion with the RS storage flip-flop. The flip-flop is a digital circuit with 2 outputs. The signals at these outputs are usually opposite. In other words, if one output is high, then the other output will be low, or vice versa. The outputs are called Q and not Q. The not Q is represented with a bar across the top of the Q. The RS flip-flop also has inputs. There is always one set input and a reset input. These are designated with the S and R. To better understand the RS flip-flop, we will examine its equivalent circuit. As you can see, the basic RS flip-flop consists of 2 NOR gates which are cross-connected. To better understand how the flip-flop functions as a memory device, we will examine this simple circuit. When both inputs are low, the outputs for Q and not Q could either be high or low depending on which gate turns on first. For example, let's assume that gate A turns on first. Since this is a NOR gate, it will produce a high output. This high is then fed into the second input of gate B. When gate B receives a high and low input, it will produce a low output. Now let's assume that gate B turns on first. When gate B turns on, it produces a high output, which is then fed into the second half of gate A. This causes gate A to output a low. This low output from gate A and the low from the set input will cause the not Q output to maintain a high state of energy. Next, we will see what happens when the reset input is low and the set input is high. The truth table shows that when the reset is low and the set is high, output Q will be high and output not Q will be low. To understand how this happens, you must first know and understand the truth table for the NOR gate. Basically, any high input will cause a low at the output, and when both inputs are low, then the output will be high. Since the set input of the flip-flop is high, then we know the output of this gate will be low. This low is then fed into the second input of gate A. Gate A now has 2 low inputs, which is the requirement for a high output. Therefore, the output of gate A will become high. At this time, gate B has 2 high inputs, which causes it to maintain a low at output not Q. And gate A has 2 low inputs, which causes it to maintain a high at output Q. This time we have made the reset high and the set low. As you can see from the function table, Q will be low and not Q will be high. Since the reset is high, we know that the output from gate A must be low. This low is then fed into the second half of gate B. Gate B now has 2 low inputs, one from the set input and one from the output of gate A. This forces the output of gate B high. As you will notice, the output at not Q is latched at high, and the output at Q is latched low. Here we have changed the inputs so that both the set and reset are high. The truth table shows that under this condition, both outputs Q and not Q will be low. This is easy to understand since we know that a high at any input of a NOR gate will cause the output of the gate to go low. The set input of a flip-flop is sometimes called the preset input, and the reset input is sometimes called the clear input. Next, we will examine the D flip-flop. The D stands for data. If you will look closely, you will see this flip-flop has 2 additional inputs. One is labeled D, and the other is labeled C. D is for data input, and C is for clock input. You will find, however, that some D flip-flops will not have the set and reset inputs. They were mentioned so you know they are available. To better understand the D flip-flop, we will examine its equivalent circuit. Notice that this circuit consists of 2 NAND gates, 2 NOR gates, and 1 inverter. We also have a clock input, a data input, and 2 outputs, Q and not Q. The clock input is a recurring signal that initiates the transitions of the flip-flop. When the data input is high and the clock input swings high, it places 2 highs at the input of NAND gate A and a high and a low at the inputs of NAND gate B. Notice the high was switched by the inverter at the input of gate B. Since gate A is a NAND gate and it has 2 highs at its inputs, we know that it will produce a low at its output. Also, since gate B is a NAND gate and it is receiving a high and a low, it will produce a high at its output. As you might recall, when a NOR gate has any of its inputs high, it will produce a low output. Therefore, NOR gate D will produce a low output, which is fed into NOT Q and into the second input of NOR gate C. At this point, NOR gate C has a low being applied at both of its inputs. Therefore, this NOR gate will produce a high at its output. Notice that the information which was present at the data input has now been switched to the Q output. Now suppose we make the data input low and apply the high clock signal. As you can see, gate A has a high and low signal being applied, and gate B has 2 high signals being applied at its inputs. The low and high condition of gate A will cause it to produce a high output. Gate B, on the other hand, now has 2 highs being applied at its inputs. This causes this gate to produce a low output. The high signal from gate A is fed into gate C. This high signal at gate C will cause it to produce a low output. The low output from gate C is applied at the Q output of the flip-flop and the second input of gate D. The low signal from gate B is fed directly into one input of gate D. Since gate D now has 2 low inputs, it will produce a high output. Therefore, output not Q will become high. By now you should have noticed that the output at Q will be the same at the data input when the clock signal is applied. As we mentioned earlier, some D flip-flops also have set and reset inputs. However, on most flip-flops, the 2 inputs are labeled preset for set and clear for reset. When the preset and clear inputs are at logic 0, they have no influence on the operation of the flip-flop. However, when the preset is made a logic 1 and the clear input is at logic 0, the flip-flop will set to its 1 or high state regardless of the control inputs and the clock. In the same respect, when the clear input is at logic 1 and the preset is at logic 0, the flip-flop will set to its 0 or low state regardless of the inputs at the data and clock. If, on the other hand, both of the preset and clear inputs are made high simultaneously, the output will result in an undetermined state. It could be high or low. Here we see a quad-type D flip-flop. This IC can be connected as shift registers or counter elements, as well as for specialized switching and timing control circuits. Even though this IC contains only 4 flip-flops with a common clock and reset inputs, there are other ICs available which will contain up to 16 flip-flops. As was just mentioned, the 4D flip-flops are controlled by a common clock and reset signal. You may also have noticed that the data inputs D0 through D3 to each flip-flop, as well as the outputs for Q and not Q, are buffered by separate amplifiers. Only during the time that the clock signal swings positive will the data which is present at the D inputs be transferred to the Q outputs. The reset function, however, is possible at any time and is independent of the clock signal. In the type D flip-flop circuit shown thus far, the data input was not allowed to change while the clock input was high. This ensured that the flip-flop was left in a definite state after each clock pulse ended. If the input information changed while the clock pulse was high, the output at Q would change correspondingly. This would cause no problem so long as the flip-flop was used only for the storage of digital information. However, the flip-flop is used for other applications where this change of state could create false information. In such applications as counters and shift registers, the change of state at the output must be delayed until the inputs are no longer sensitive to change.